Well, I'll wait till next period to comment on the examination, but except to say that the first problem obviously is an azeotrope at about 54 mole percent of ethyl acetate, where the liquid and vapor composition are equal, and the temperature is a minimum of 71.8. And since that there's no extended region of the liquid composition in which you get a constant vapor composition, at least from the data, why it would be presumed to be a homogeneous azeotrope. Although it's possible that you could have had a heterogeneous azeotrope here, but you couldn't infer that from the diagram. But if there had been some intermediate points, there could have been a short region of heterogeneous azeotrope.
How long does that? I mean, it was flat, or essentially flat for, it was 71.8, 71.8. I mean, it was constant for a few degrees. How long did it constant for a few?
Well, that's the fact that the temperature there was the same for two values of the liquid composition. This is actual data now. This is not a hypothetical case. It's actual. So that means it's probably correct to the nearest tenth, but then there would be at 50%, there would have been a slightly higher temperature than 54%. But well, if you've made that, if you misinterpreted that point and gave me the reasons, I'll consider it. Now, I have some material here I wanted to discuss with you today, and since we don't have much time left, I prepared it on a handout here, so we can cover the lecture in about 10 minutes, I guess. At least save the time I would have used to writing on the board. Before I start, however, I'd like to begin thinking about the fact that we'd indicated we'd have a field trip if we could work it out.
We don't have a field trip.
And the problem is, how can we arrange a time where everybody could go? Preferably, we would go in the afternoon, let's say about 1 o'clock, but I know several have the conflicts in the afternoon.
What day in the afternoon?
On Wednesday.
Well, preferably be Wednesday, which would coincide with our own periods, our own schedule. But I'm willing to go any other day. Now, of course, it's pretty hard to get a consensus here right quick. And I suppose the only other day would be a Saturday. But
I work Saturday.
I work
So do I.
Everybody works on
well, let me see. Let me have a show of hands as how many could go possibly next Wednesday afternoon, starting at 1 o'clock. Yeah. How many cannot, in other words? Just 4. Huh? Well, I'll see if I can arrange it. So, in other words, it would be somewhat desirable to go within the next 2 weeks in order that the weather is still pretty good and perhaps they're still operating at one of the plants we would visit.
It should be in Lodi.
Yeah, Lodi is the closest place we can go to see any distilling and brandy operations, and so that's where we'll go. Well, I'll let you know Tuesday morning if that's, well, I'll try to work it out for next Wednesday afternoon. All right. Last time we were discussing about the parameters that one needs to consider in designing a continuous distilling column in order to affect a given set of requirements. And I wrote down on the board a group of parameters which included number of plates or ideal stages, the size of the column, and the column internals. And the fourth area of parameters would be accessory equipment. Now, I want to discuss now one of the methods, one of the more common or useful methods for determining the number of ideal stages. Let me say that there are about four or more methods. The first of which is, the earliest of which for calculating number of stages required for separation, known as Sorel's method, S-O-R-E-L. And this was a method based upon making calculations from plate to plate, tray to tray, using both material and energy balances, or enthalpy balances, from which the quantities of liquid and vapor and the temperature on each plate and the compositions of from each plate were calculated. Now, obviously, this is a pretty laborious and extensive type of a treatment. I think Sorel lived in, or did this perhaps along about 1890 or something like that, maybe 1900 in that period. Then a little later on, Lewis in this country made a modification of Sorel's method in which he made the basic assumption of equal molal overflow, as it's called. Equal molal overflow, which means, as I'll elaborate a little bit more later, that you have on a mole basis, pound mole basis, you have a constant flow of liquid from tray to tray, as long as you're not taking something out or changing the situation. But anyway, in a given section, you have a constant liquid flow rate. Now, and also next time I'll give you some an enthalpy or heat energy chart which will justify this assumption, show that it's justified within reasonable limits. This assumption of equal molal overflow implies that there are equal molal heats of vaporization for various mixtures in the column, not only the pure components, but mixtures thereof, that there are no significant heats of mixing, and that molal heat capacities and specific heats are either essentially the same or negligible difference. But even with that assumption, it still required calculations from tray to tray. So if you had theoretically, if it comes out to be you're going to have 20 trays, you'd have to make 20 separate calculations. And this would be very difficult manually, although it's tedious and essentially involves a lot of trial and error. But this and the Sorel's method are still used somewhat where they have the computers available to do the calculations. Then we come to graphical methods, of which the one I'm going to talk about is called the McCabe-Thiele graphical method, that which your handout is about. And this also is based on Lewis's modification of Sorel's method, that is the assumption of equal molal overflow. There is a fourth method, or a second graphical method, is called the Ponchon-Savarit. S-A-V-A-R-I-T. And this makes no assumption of equal molal heats of vaporization, but is a graphical method which incorporates whatever variations in molal enthalpies or heat contents exist between the vapor and liquid. And graphically it requires the construction of an enthalpy concentration diagram for the binary system in question, which is then worked in conjunction with the equilibrium curve. So that method is explained in standard texts such as Winkler book. Which one is it? What's the name of that? VEN140. I'm getting the two mixed up. And And also, it's the primary basis or method illustrated rather clearly in that book by Brown, The Unit Operations, a big book that I've brought in a time or two. It's on reserve here. But anyway, the McCabe and Thiele method will be sufficient for our purposes, and you may think that's complicated enough. Anyway, on the handout I gave here, first of all, you see I drew a little sketch of a column and put some symbols on it. We use a symbol V to represent vapor rates on a molal basis, and L on the molal liquid rates, and put a subscript down to indicate the number of the tray. Like V sub 1 would be the vapor leaving tray number 1, and L sub 1 would be the liquid stream leaving tray number 1. Another assumption, which is not specifically stated in this handout, is that we make the assumption that the vapor evolved from the tray is in equilibrium with the liquid leaving the tray. That the vapor leaving the tray is in equilibrium with the liquid leaving the tray. As I indicated in the laboratory to some of you yesterday, this is not always the case where you get a liquid gradient across a tray, particularly true of large diameter trays, but for the purpose of the calculations and calculating the ideal stages, we make the assumption that that the vapor has been evolved in the equilibrium conditions from the liquid. Then so then in this little diagram we can number the trays as it's numbered here from the top, 1, 2, 3, and then we'll just use a symbol N to represent any tray in the concentrating section. Similarly, below the feed tray, in this particular case, I've used the V prime symbol to indicate the vapor rate, and the L prime to indicate the liquid molal rate in the stripping section. And we use the word M to denote any tray in the stripping section. And M plus 1 would be, of course, one tray below. So now the way we arrive at some relationships which are designed to determine the relationship between the Y, or the vapor composition of a stream that's interacting with the liquid on that tray, as affected by the process conditions, or that is particularly the reflux ratios involved. Why then we resort to our old familiar trick of writing material balances. So looking at that sketch there, we've drawn a little dotted line around, encompassing the top of the column and the condenser and tray number N. And so there, if you equate what leaves the system to what enters the system, you'll see that the only thing entering the system is V sub N plus 1, entering down at the bottom of tray number N. And the only thing leaving the system, indicated by the dotted line, is the liquid flowing out of tray N down to the plate below, and the distillate at the top of the column from the condenser. And so with that basic assumption, the basic equation of material balance, then we multiply by the concentration to get the component balance, and get an expression there which I won't read off again. But you can see what it is, that, and then making the assumption of equal molal heats of vaporization, we then say that the vapor rate leaving tray N is the same as leaving tray N plus 1 is the same as N plus 2, so we just drop the subscript and just call it plain V. So then the equation then simplifies to what I've written there is number 1. Y sub N plus 1 is equal L over V times X sub N plus D over V times X sub B. X sub D. Now you see that for a given specified conditions, L over V would be a constant. It would be determined by the reflux ratio, as you could readily see. It's what we call the internal reflux ratio, or the ratio of the descending liquid to the ascending vapor. For example, if we had a reflux ratio of 2 to 1, meaning external, we'd have means that we'd run back 2 moles of L for 1 of D. And since the vapor has to equal the sum of those, then V would be equal to 2 plus 1 or 3. So the ratio then internal of L over V would be 2 over 3, or 2/3. So then we come to equation 1. So that's, you see, is an equation of a straight line.
Yeah, could you go that one last
I'm going to run out of time here before I get. All right, if we have, if this is the condenser here, and this is the top of the column, and we're taking out distillate here, and we're running the rest of it back as liquid, but this is supplied by vapor. So obviously this vapor stream condensed becomes split into L plus D. V is equal to L plus D. So if L is equal to 2 times D, or let's say let D equal 1 and L would be 2. If L is equal to 1 and D is equal to 2, no, the other way around. L is equal to 2 and D is equal to 1. We say it has a reflux ratio of 2 to 1. Or the external reflux ratio was 2 to 1. But the internal, what I call the internal reflux ratio, would be equal to L over V, and L is 2, and V is equal to L plus D, or 3. So it would be 2 to 3. Is that right? Okay. In other words, in every case, what we're really interested in is the ratio of L over V, whether it's this particular column or any other column or any section of the column. Well, anyway, we have equation number 1 then, and I'm going to have to stop, and that's it. You can see that where y sub n plus 1 and x sub n are the only variables, it's equation of a straight line of slope L over V and some intercept value, some value that could be determined by intercept. It can be shown by letting y equal x and solving that it passes through the diagonal at a value of x sub d. And so, similarly for the stripping section, we write a material balance around the bottom part of the column, as I've done on page 2, and making the simplifying assumptions, we come up with equation 2, which is called is also a straight line. It's called the operating line for the stripping section. And we don't have time to go into the feed tray conditions, but you can read it there. You can see that the relationship between the vapor in the stripping section and the rectifying section, and also the liquid, depends on the feed conditions. If you introduce the feed as a boiling liquid at vapor saturation temperature, for example, well then it's just going to boil when it gets in there, and go ahead and add more liquid to the feed tray and not affect the vapor rate. But if it's a cold feed, below its boiling point, it's going to condense some vapor at that point, and hence it'll decrease the vapor passing through, but it'll increase the liquid on the tray and cause more to run down. And so this Q term is introduced in here as a convenient way to represent the relationship. And the Q can be determined by some considerations of heat balance and enthalpy.
I think we ought to read this over once and come and ask questions next time.
Okay, that'd be a good suggestion for others. This particular material can be found more elaborately described in the standard textbooks.